All right, so moving on to chapter 14, we're going to start talking about acids and bases. And so let's talk a little, just a tiny bit about the kind of history. So when acids and bases first started coming around, there was the Arrhenius definition. So this was the first guy that said this is an acid, this is a base. And what he said was an acid is something that produces an H plus in water, while a base produces hydroxide, OH minus, in water. And so he was specifically talking about water, but later on we learned that we can have acids and bases in all kinds of different stuff. And so out came the Bronsted-Lowry definition. And this is probably the one that you're familiar with, and this is the one that we'll focus on in this class. And so Bronsted-Lowry definition says that an acid is an H plus donor, so it gives up H plus. And remember, H plus is hydrogen without its electron, so it's essentially just a proton, And then in a base is an H plus acceptor. So the acid gives an H plus, the base takes away an H plus, right? And this is what we'll be talking about. Although most of our examples in Gen Chem will still be in water, so they do fit the Arrhenius definition. However, if you move to higher levels of chemistry, such as organic chemistry, you'll be talking about a lot of other different solvents other than water. So let's just take a look at a basic example. So here we have HCl plus H2O. And in this case, the HCl, hydrochloric acid, is going to act as the acid. And so if we take a look at where this H is going, it's going to move from here to the water to form H3O plus Cl minus, right? So you can tell that an H plus moved, right? Not, and it's just the H plus, right? None of the electrons. The electrons from the HCl bond went onto the chlorine. And so this donated the H plus, so this is the acid. The water accepted the H plus, so it is a base. And then here we have NH3, ammonia, with water. And ammonia and most nitrogen-containing compounds are actually basic. So in this case, one of these waters will go, or one of these hydrogens, one of these H pluses from the water, will go from the water to the ammonia. And so in this case, the water is acting as the acid, and then the ammonia is acting as the base to form ammonium, so NH4 plus OH minus hydroxide. So you can see here water can act as an acid or a base, but basically what you want to do is you want to look at the overall equation and ask yourself, where is this H plus going? The thing that's giving up the H plus is the acid. The thing that is accepting the H plus is the base. Here's just some list of some common acids, right? They're used every day. We have, hydrochloric acid. That's probably a pretty common one. Some acetic acid. That's the main component of vinegar. So anytime you're drinking vinegar, you're drinking acetic acid. Citric acid is found in citrus fruits, so that's everywhere. Carbonic acid is what's in your soda. So that's a good example. And then on the right, we have some bases, right? We have some hydroxides, right? That's obvious to tell that this is a base. Then we have bicarbonates. So those are basically carbonic acid without the H plus. And then we have ammonia. You definitely want to know that ammonia is generally considered a base. It's a very commonly used base. And then here's just a picture showing the Lewis structures of some acids. So here's hydrochloric acid, obviously up there. And then you've got some kind of strong acids, what later on will be known as oxyacid. So you can look for an OH bond. Anytime you see an OH bond, that probably gives you a good idea that it's going to be an acid, right? Especially if there's a carbon and then a doubly bound oxygen next to it, right? So this kind of H, O, some element here, and then double bound O, good chance here that this is going to be an acid.